Be kind to each other. We're all just here to chat about fun science. So let's have a great time today. So first today we have Suchindram talking about modeling higher order modes and memory with the backwards one body formalism. Go ahead and take it away.
Thank you. Hello everyone, my name is Suchindram. I'm a graduate student from West Virginia University, and it's a great pleasure to be talking here today about my work improving the backwards one body merger ring-down model and applying that to memory. And it's an especially awesome coincidence that my talk is kind of a prelude to two additional talks you'll be hearing later today in this session. So it is an extreme privilege to be able to lead this or start this session. So just to give you a brief overview of what I'll be talking about, I'll be introducing what the backwards one body.
This is not muted.
So I'll be introducing the backwards one body formalism, and I'll talk about extending that to higher order non-equatorial modes, and eventually I'll end by explaining how we apply that to gravitational wave memories. So what is the backwards one body model? It is an analytical first principles merger ring down model that has been vigorously tested against the 2-2 dominant mode of emission. It's rooted in first principles derived from perturbation theory, and it natively models the spheroidal modes in the coprocessing group. Sorry, I don't think the clicker's quite working. Oh, there we go. So, Bob is fundamentally a merger ring-down model, so you have to combine it with an in-spiral model. And since it is an analytical model, a very natural choice is to combine it with EOB, or effective one body. And so this is exactly what Siddharth Mahesh, Sean McWilliams, and Zach Etienne did in this past year, where they released this model known as SEBOB, spinning effective to backwards one body. And essentially it combines SUB NRV5 with backwards one body. And they tested this against a whole slew of NR cases, and they found that it's very accurate, comparable to SUB and RV5, but one of the key advantages is that it requires far fewer tuning parameters to NR. So it requires 6 fewer tuning parameters than SUB and RV5. So that is a step closer in the direction of a more first principles model, and it is highly fast, so it can be computed very easily. So the backwards one body model has been tested against the 2-2 mode especially, but what about higher order modes of emission? And this is kind of an unanswered question. We know that it natively models spheroidal modes. So the question is, okay, first you have to decompose spherical modes into spheroidal modes to be able to compare against NR, right? And then after that, you have to see, does that model, is that model consistent with what NR chose? Oh. So, I didn't realize I was so quiet. So basically, these spheroidal modes need to be tested for these L not equal to M modes. And one of the big questions that I had was, is there a first principles extension to Bob that can model the 2-2 mode, 3-2 mode, and the 4-3 mode robustly? And the answer is almost. It is currently a work in progress, but a large step has been made in recent weeks. So basically, to model higher order modes with Bob, one way to do it is by making corrections to Bob based on quasi-normal mode excitation factors, as well as the Sasaki-Nakamura formalism. I won't go too deep into the details of the corrections I made to the Bob model, but essentially one of the discrepancies of the original Bob when applying it to spheroidal modes was that it was a bit too broad, meaning it overestimated the total amplitude a little bit past the peak. But after applying a physically informed correction, you can actually recover NR spheroidal modes. Oh.
Sorry, you're echoing.
Yeah.
What did you have open for? Not my person.
Okay. Okay, nice. No. Applying this correction, so this plot on the right here basically shows 430 mode for math ratio 6 system. SXS, this is from SXS catalog, so green here is SXS, and the dashed black line is the newly improved Bob model. And it works very, very well in modeling the 430, and I'll show you in the next slide as well, the 320 mode as well. But there are caveats to this. One is that we can reach high accuracy, but I had to introduce one additional NR tuning parameter to Bob, which ideally I wanted to avoid, but that's currently part of what I'm working on. I'm trying to, avoid NR tuning parameters. But moving on ahead, we see here on the left side, this is the 320 mode from the same exact simulation, and it also behaves very well with backwards one body. And we basically just fit, or not fit, but we set Bob to the NR peak. So it is equated to NR peak, and then it carries the rest of the waveform. So now I want to transition into just talking a little bit about memory and how I applied this model to memory. So memory is a permanent displacement of test masses following the passage of a gravitational wave. The type of memory I'll be talking today is about nonlinear memory produced by the flux of gravitational waves themselves. And this memory effect, if you choose the right coordinates, is dominant in the 2-0 mode. And so one way to incorporate memory, or incorporate Bob to model memory, is to use this formula. This is a memory formula that was basically derived by Jann Zosso and collaborators in February of this year, that essentially gives a nice closed form equation for modeling memory. And you can plug in basically different modes of emission to get a memory waveform. And what's nice about this is that you don't need to kind of use like BMS balance laws, which is traditionally used for memory, and you don't have to try to optimize for those kinds of laws. So when we apply that to Bob, we basically get a very close memory waveform to NR. So this is the 2-0 mode memory. The blue here is memory from the SXS catalog, calculated using BMS balance laws. And the black is the Isaacson approach to memory formula applied with the backwards one-body model. And what I did here was I essentially set the in spiral to be NR, so up to this gray dashed line is SXS, and then past that is Bob, and it works very, very well. So a lot of this is work in development. What really needs to be done is test this against a whole suite of more simulations and see, is our model truly robust? My preliminary work has suggested that it is, and that it is both accurate and close to a first principles model, and that in the future, when we want to fully make use of this model, we really want to combine it with EOB. So SUB and RV5 already gives us the 3-2 spherical and 4-3 spherical spin-weighted spherical modes. And so in the future, my plan is to incorporate that with SUBNR and make a more robust SEBOB waveform model. And one other thing that needs to be mentioned is that memory is a large part of the 2-0 mode, but the 2-0 mode also has this oscillatory component. And so in order to model that, you need a model for that oscillatory component. And something that I've been working on the side was trying to model psi2 analytically and applying that to Bob. And basically, this psi2 model can be applied to generic waveforms, but it's still somewhat phenomenological. I've been trying to prove it from first principles, but basically you can use that to get psi2, and then from psi2 you can derive the oscillatory component of the 2-0 mode. with BMS balance laws. And a sneak peek of that psi2 model is right here. This is psi2 from, you can barely even see it. The blue is behind the red here. It's the CCE catalog psi2 waveform data. And plotted against it is it's a one parameter psi2 model using the backwards one-body model. And I combined it with NR at the peak, so NR modeled in spiral and backwards one-body to merge a ring diagram. So yeah, that is what I've been working on, and I'll be happy to take any questions.
Great, thank you. Any questions? Please come to the center.
Hi, thanks.
Oh, I might need to just hit turn on.
Hi.
Yeah, yeah.
Thank you for the very nice presentation. I would like to ask you, what is YLM infinite that you have shown?
Oh. Yes, so this YLM infinity is basically the parameter we're using to correct the late time tail of the Bob model. Basically, when you model Bob for news, it overestimates the late time waveform. This is still currently phenomenological, but I've been investigating ways to remove that phenomenology and eliminate that NR tuning parameter altogether.
And last question, if I'm allowed, is just to ask, is there, maybe you could summarize quickly, how can you add more physical effects to Bob? Because I guess this is just for quasi-circular liner spin, and then go to spin precession and eccentricity. If you could comment on that, thank you.
Yeah, so yeah, spin precession with Bob is still an open problem that needs to be developed of processing Bob model. One of the ways I was able to introduce more physicality here was by relaxing some of the assumptions Bob made and applying a more rigorous derivation that doesn't just nicely go into a single hyperbolic secant profile. But yes, it's a combination of relaxing certain assumptions put into the original model.
Okay, great, thank you. Any questions online? Okay, then fantastic. Let's thank Suchindram again. And thank you for your patience. Give us just a minute to, go ahead and come up, but we just need a second to figure out. Okay, great. All right, we are on to our next talk of the day. So we've got Parthapratim talking about the high mass ratio challenge in gravitational waveform modeling. Here you go.
Thanks, Deborah, and thanks the organizer for hosting the conference and giving us opportunity to present this work. So I'm a postdoc at Cardiff University with Mark Hannum, and in this talk I will mostly emphasize one of the major challenge in waveform modeling with Lisa binaries. So we know that Lisa will prove a vast variety of binaries and like intermediate mass ratio in spiral, extreme mass ratio in spiral with mass ratio ranging from 10 to billions. And we can do interesting sciences, both astrophysics, fundamental physics, but to achieve those scientific goals, we need to characterize the sources very accurately, and for that we need waveform models. So what is the challenge? So we know that we need numerical relativity simulation of binary black holes at the Leydig spiral merger and ring down of the binary black hole mergers. But to date, we don't have no inertior models beyond mass ratio 10 for processing binary black holes. But that's fine for current observation within LVK, because we pretty much observe equal mass, mostly non-spinning binaries. So the most asymmetric binaries we have observed so far is 1914, which was small spinning and mass ratio of 10. But for Lisa, it's different problem. We can observe from 10 to billions. But then the question is how difficult is to do numerical relativity simulations for this mass ratio. And so typically the computational cost naively goes over Q square with the mass ratio, because for mass ratio, large mass ratio binary, you have many more cycles and you have to also resolve the small black hole. So it's naively Q square, but there are also other factors as well. So if you go to section 4.4.5 of the LISA waveform working white paper, then you can find it. But in that equation as well, there are a few missing factors. So it's just a lower bound. And it turns out that the current codes, existing codes, are incompatible to produce binary black hole in that regimes, and fancy and numeric GPUs are not enough. So producing high mass ratio binary black holes with generating spin orbital property is a major challenge in the field. So we asked the questions like how accurate our current model is to high mass ratio. So to do that, we do in our simulation of processing binary black holes of mass ratio 18. So 18 is not a crazy number because it corresponds to symmetric mass ratio of 0.05, and that was produced for developing phenomenological model and so on. And these simulations have primary black hole with spin of 0.8, and the secondary black hole is non-spinning, and we take 5 range of misalignment angle with the orbital and global momentum. And these are log simulations and 15 to 25 orbits before merger, and you can see the waveform from this. But these are scaled to 150 solar mass, but you can see the modulation pattern. It's a rich modulation with high harmonic feature and precision, and these are pretty complicated compared to equal mass binaries. But these are also expensive, so it takes 20 million CPU hours to produce those. And these simulations are produced by BAM code, which is based on BSS formalism and finite difference code itself. So here is the comparison between state-of-the-art model used in LVK analysis with our NR data. So we have phenom model, both frequency and time domain state of the model, then UOP model, it's a time domain model, and then surrogate, but surrogate is, you can't call surrogate up to that happiness ratio, so we compare the NR data with those 3 models. And in these plots, what is shown is the plus polarization, and the black curve is the NR, and the colorful graphs, those are models. And you can clearly show, right, these are crazily different, right? Of course, this is pretty close because it's a less number of samples, but this is quite different, right? I mean, of course, the models are, the models at this parameter values does not look equal mass binaries, but it does show a lot of modulation, but it's very far from the reality. And this is these are all the results I will show for LIGO, because we did the analysis in the LIGO frequency band, but this will be more problematic for LISA, because LISA we have many more cycles and probably more louder as well. So one of the way to quantify how bad or good your model is to estimate mismatches with the waveform models. So we did this analysis with these 3 of a model. So it's shown here. So whoever works with mismatches can identify these are pretty bad mismatches. And if you want to connect it to the signal to noise ratio or the loudness of the signal to these signals will be distinguishable or indistinguishable, then this line corresponds to actually SN12. So it's a very minimum, right? And I mean, you know, this is a naive measure, but I mean, this is pretty bad mismatch. I mean, it will be even problematic with LISA. And this is the result for from the parameter estimation, but this is again a LIGO. The take-home message from these plots, as you can see, that none of the model can accurately capture, because we already signed the comparison of the model strain with the So one thing you should not do from this plot is that you should not compare with model performance between different models. You can, in this case, someone does better, and if you go to other case, that waveform model does worse. So it just models bounce around each other. So you should not take that, but the take is pretty bad. But you can kind of connect that the numbers from the previous plot, which are the SNR 10 and 12. So at that SNR, the models won't be biased. So here we kind of produce three simulation of one of the configuration. We produce three different simulations to understand the convergence of the code. And here again the mismatch between different resolution is shown there. So as you can see, they are not great. So it's even if it takes 10 million CPU, they are not that much accurate in our simulations. So one thing I want to emphasize is that so again, the way we now kind of estimate the distinguishability criteria, right? We translate mismatch to the SNR bias SNR, and it turns out that in this case, I think it's around 10 or so. But if you look at the PE, so this is PE with SNR 50, the model is still indistinguishable, right? So the blue and the green in 144, 172 just lies top of each other, right? 120 is visibly it's distinct, but still not indistinguishable at SNR 50. But the mismatch prediction gives 10, right? So wrong. The mismatch, the way of calculating mismatch and then translating to the bias SNR, those types of things are not accurate. Maybe good enough for order of magnitude estimate, but for precision science goal, which will have LISA, because we will have a more loud signal, more signal, we still yet don't know how to, what is the accuracy measure for waveform model. And in there, we don't know actually how inner errors translate to the model. So here, this is my last slide. So I just summarized the challenges in this challenging parameter space. So Florida simulations cost scale with mass ratio square and simulation length, accuracy requirements, and we need insanely accurate waveform for LISA if you want to extract science goals like fundamental science and so on, test of GR, etc. And can NR achieve 10⁶ more efficiency? And so we probably need different formulation of our current code to achieve this goal. And also the IMRI, if you have high mass ratio, you need more multiple moment will be excited, right? So the current NR code probably goes up to 8 and 10, but you will have up to go to many more multiple moments to extract. So we need to work on that as well. And we also don't know like how many multiple moments, and that's also need to be understood. And then accuracy measure. So we don't have a understand like how the mismatch or how if we have a waveform model to tell when in the parameter estimation process it will be case bias. So we need to develop tool to understand that. And secondly, we need to know how NR error propagate to the waveform model. So the case I have shown it before, I have shown that the models, the errors are quite orthogonal to the model surface, and that's why even if the mismatch between different resolution is bad, but in the PE waveform model does not see it, they see the same waveform. And so if we don't overcome these challenges, there are many LISA science goal can be compromised. So I'll stop there. So this is the talk is basically emphasize some of the major challenges in the high mass ratio. And thank you for your attention.
Okay, great, thank you. Can we have questions come to the, go ahead and come to this intern, just get in a line. Great, thank you.
Why?
Oh, we got to turn it on.
I can't see. It's too close to me. Why does the cost scale as the mass ratio squared and not cubed? I would think it would be the volume of the smaller object.
So one thing is the number of cycles, so that kind of go over Q for high mass ratio. The second thing is like, so you have to resolve the smaller black hole, right? So to do that, you need to Q times more resolution. And this is a naive measure, but there are many other factors which are not taken into account.
Right, so that one is cubed.
Yes,
Result.
Q and Q square, yes.
Yeah, so I was very interested in your previous slide with the fact that the NR errors were, for some reason, coming out to be nearly orthogonal to the signal manifold. I'm wondering, do you have insight into that? Is that like just a happy coincidence, or is it somehow that, the things that get missed in the simulation, it's because somehow those are directions that aren't well constrained, and they also just aren't directions that actually matter that much physically? I mean, is it a coincidence, or is it actually expected because, those just don't matter, so the NR doesn't see it either, and so it isn't constrained in the NR simulation?
So short answer is we don't know.
Sorry?
We don't know yet.
You don't know?
Yes.
Okay.
So, yeah, this is one key point we need to understand, so that we can produce an error up to that accuracy. Maybe we don't need that much high accurate.
Yeah, you'd have to be happy with that. You would want to know that there was a reason for this and it wasn't just a fluke.
So it's basically the interplay between how waveform model manifold interact with inner surface. So those we don't understand. I mean, I already mentioned that we don't have good accuracy measure to precisely pinpoint at a certain if you have a model, then at what SNR you will see biases. I mean, we have some estimates what are magnitude that tool, but we don't have a till accurate pinpoint tools.
Any questions online? Okay, I think we have, okay, if they're fast, we can let's do the one behind you first. Oh, you're just coming up, great. There you go.
Still on? Okay, just a quick question for you. I'm just wondering, as you go to the higher mass ratios, if there's thought or discussions to bring in the self-force calculations to bridge that gap so that the NR can focus more near merger where it's really needed, where, because it looks like the self-force can get down pretty far. So just wondering if you've thought about that.
So we need sort of validation. I mean, of course, NR is needed probably for short duration, and then probably self-force will, or maybe some other EOB model will get, but we need sort of validation. We don't know. Like, for example, in LVK analysis, we're supposed to do like inspire is post-Newtonian or EOB will do, but then there is a region we don't know. I mean, there is no certain definition cutoff, right? So precise cutoff when to trust one and when to trust. So we need some NR sort of because of validation.
Okay, thank you.
Okay, great. Let's thank Parthapratim again. On to our next talk by Sean Williams. We've got towards more robust generic spinning gravitational waveform models, including higher modes with the spinning effective to backwards one-body paradigm. Take it away.
Thank you. And I advance on this one, right?
Yeah, and that clicker should also.
Oh, this one does? Great.
Should be able to click up.
Okay. So this is work that's done with a whole bunch of people. So Sid Mahesh, who just recently completed his PhD, is really the main developer of SEBOB. But then our whole group at WVU, Anuj Kankani, you just heard from Suchindram Dasgupta, and then Shay Reddy and Zach Etienne at University of Idaho. That's fine. Okay, so, right, why do we care about, this somewhat pedantic level of accuracy that we're talking about? Well, Lisa is going to see these signals outrageously loudly, and so to actually milk all the information that we can possibly get out of these things, we really need to nail these signals down. For the sort of golden sources or whatnot for things like testing general relativity and such, the merger in particular is going to be really loud. So that is the particular place of emphasis. The in-spirals are very accurate, even the very long ones can be modeled pretty accurately. Our limitation really for those signals that we want to absolutely nail is in the late stages of merger into ring down. So the way we tackle these things, you've already heard about a few of these tools, right? So there's a lot of different tools we can sort of throw at this, and as I'm going to go off script, because as I was sitting here listening to questions, I thought about there's kind of this famous like Ed Witten talk on M theory, right, where there's an elephant and each one's pulling out a different, these different other theories are all sort of showing an element of this unknown true underlying theory. This is, I think, better motivated than all that. But regardless, it's, a bunch of different tools: black hole perturbation theory, self-force, EOB, regular old post-Newtonian, Bob, right? These are all different levers, and I think they're all giving us different amounts of information, and we're progressively being able to sort of eliminate the physics-free, right? Numerical relativity is wonderful. It doesn't tell you why the answer is what it is, right? It just gives you the answer, right? It doesn't really, I mean, you can gain physical insights by looking at data in different ways, but there's lots of subtlety and challenges of if you look at local quantities, it's gauge dependent, and things like that, right? So we really want to try to throw all the physics that we can at this to really understand, okay, we see a signal, what is that actually telling us about dynamical spacetime? So SEBOB, we're trying to position as sort of a hybrid that's pulling in information from all of these things, and the hot off the presses things that you heard Suchindram talk about, right? We talk a lot about self-force in our group meetings. We talk a lot about black hole perturbation theory, right? We're trying to bring all these tools to bear to really minimize the amount of throw up your hands and do a lot of numerical relativity simulations and then just calibrate, right? Which we're going to have to do. I doubt we're going to have a first principles model that's accurate enough for these purposes ever. But we want to minimize that so we get as much physics understanding and insight as we possibly can. Okay. So in case anybody in here, and I'm going to go briskly through this, right? But the idea with effective one body, which is similar to, it's a similar motivation behind Bob, is taking the regular two-body system and just like in Newtonian dynamics, right, you map to there's a reduced mass orbiting around the total mass located at the center of mass, that kind of thing, right? This is the relativistic extension of that, right? So instead of having a two-body system that's expanded in post-Newtonian and it's some long, complicated series in powers of V over C or whatnot, right? We try to map it to geometry. We say, okay, this is, a test mass moving around following a geodesic in some effective space-time. So that's the very high-level idea, but there wasn't really a merger part, and that's where Bob is going to come in, but stay tuned. So in the GR one-body problem, the way we do this, right, and a little bit of math, but not much, right, so you can introduce an action, right, and have a Lagrangian and have Lagrange equations of motion, just like you've done in classical mechanics. We have the mass shell constraint, and so we can instead treat this with a Hamiltonian, and this is the conventional way that things are done. And so, for example, for Schwarzschild spacetime, right, you can write down a nice, simple, clean Hamiltonian, and you have an effective potential, and it tells you where this go is, and you write all these critical orbits and such. So it's a nice clean physics picture of the dynamics that's going on, and right, it's the analogy to the Newtonian dynamics, where you look at the effective potential and you understand why the orbits are doing what they're doing, depending on where the energy is relative to the effective potential, right? So it's a nice physics-first approach. Right, instead of the PN approach of expanding in a series, right, you have some sort of effective Hamiltonian, and the main point of this slide is to emphasize it really is effective, right? It's not the necessarily meant to represent, like, if you could take a spaceship and fly up to the system, this is what this thing looks like. But it's the Hamiltonian whose evolution gives you the physics that you want for the system that you're interested in. That's like the EOB sort of approach to things. And so recasting the whole system as an effective, single particle moving in some sort of effective background. But that doesn't bring you all the way, right? It would be great if it did, if there's this nice, clean, effective one-body way of understanding the physics got you NR level accuracy waveforms, but it doesn't, right? So, but you can calibrate. You can introduce different degrees of freedom, introduce things like the non-quasi-circular corrections. At the end of the day, you're introducing phenomenological parameters that you then tune to NR. So our group's sort of whole emphasis is trying to minimize the amount that we do that. Because that's what I say, it's like you're throwing your hands up and you're like, you lose physics the more you do that. And so we've been pretty successful getting rid of a lot, like half of those degrees of freedom. And so now we're sort of crunching away at the other half. Okay, so Bob, you already heard a bit about, right? But it's very physics first. The L equals M modes, it's super simple and clean. You can write down an amplitude for one of the metric quantities just based on geodesic deviation. Not only is it closed form, it's a hyperbolic secant, it's the simplest thing. You can then calculate a frequency based on that amplitude evolution, right? And it's all, if we're attaching to an in-spiral, then the only thing you need to know is what is the end state, what's the remnant black hole that gets made after the merger. And so sort of the key insight was, right, the merger kind of knows where the space-time's headed. It's really locked into, it can only oscillate in, much like the quasi-normal modes, a set number of ways relative to what the parameters of the final end state are. So there was a question about eccentricity and precession, right? To a large extent, the space-time can't do what it does in the in-spiral, where it's like frequency goes up and then it goes down and it goes, right? Once you get into the merger, you're kind of locked into a monotonic evolution. Frequency is just ramping up. And so the only freedom is, right, it's like, again, completely like the quasi-normal modes. There's only a set number of ways that the bell rings, right? And the only freedom is how loudly do you excite those different modes of the bell. That physics that is very much true in the quasi-normal mode picture. Bob's key insight in non-SOTs is it's also true during the merger, right? So, and that general approach has worked pretty well. So SEBOB is just taking the EOB in spiral and replacing the merger ring down, which in the EOB approach, the merger ring down model is a lot of calibrating coefficients. It's just there's not much physics. No offense to the EOB folks, there's not much physics in the merger part. It's just tune. So Bob gets rid of the merger ring down part of all that tuning for the L equals M. May have to reintroduce some to really nail down the L naught equals M. Though we're talking, again, because we're trying to make very, very precise models, like out of the box, Bob does well enough for LIGO purposes and future, any time in the near future. But when we're looking at LISA, we really have to nail this down even better. Okay. Not only do we have to be really accurate, but we have to be very fast. And so this is where Zach Etienne and his group comes in. They have this beautiful infrastructure that is motivated by making efficient numerical relativity codes and simulations. But the infrastructure is great for any purpose because you can just code up the physics in Python and it does all the common sub-expression elimination, all, right, the usual, what used to be, hire a computer science guy to write your code right so that it does things efficiently. This does all of that. And it spits out highly optimized C code. So we built this all into that, and it's all open source. And so our code is also open source as part of that package. Pip installable. Right, you saw the left plot from Suchindram. The end result is very accurate. It's also very fast, and that right plot is from a paper, but I have, for instance, on my laptop, TEOB in spiral that makes this even faster, right? We haven't fully saturated the efficiency thing, and we're already competitively fast with the fastest models that are out there. What are we actively doing right now? I mean, we have a tool that's very usable. This is in particular for aligned spin systems, higher harmonics, whatever you want. Now we're trying to push the higher harmonics even higher. Numerical relativity has a hard time nailing down the higher and higher you go. And Lisa, again, could potentially see these very high index higher harmonics, and so trying to push this even further. Precession and eccentricity, again, so we actually, Suchindram has the frame transformations already in NURBI. We don't have the NQCs, that's the missing piece, and so that's an element that we need to work on, but we're actively on it. Right. Part of NURBI is also the black holes at home code, which is super efficient, crowdsourced code, so it's like it's going to operate like SETI at home, where you can donate your CPU cycles and whatnot, and it's just going to generate enormous catalogs, and it can be run on a cell phone. So you can run a full numerical relativity simulation on a cell phone, right? So it's going to be a great tool, and we're linked in by using this infrastructure so that we can, whatever calibration we do have, we can sort of online in real time calibrate and get better and better and more accurate. And we want to push on, like I said, we're using tools and looking at self-force and all of these other tools. Part of the reason is to be able to push into the intermediate mass ratio regime, right? There's no reason that this sort of physics approach can't. In fact, for some of the modeling that goes on, it's better motivated as you move more into the inward limit. So trying to gain insights and bridge the gap better there, so that SEBOB will be able to handle, Q of whatever you want to throw at it, Q of hundreds or thousands or whatnot, and be just as accurate. So that's the objective. I think that's it. Yeah.
Great, thank you so much. Questions, please come to the center. We've got a couple minutes. Okay, well, I've got one to start us off with. So you were talking about how, like, the merger itself is surprisingly simple in that you really just have things like monotonically increasing frequency. Well, first off, it's interesting to think of that way, because typically we think of the merger as the most complicated. But how exactly then, when thinking about that and trying to simplify things, when would you define the merger as starting for that idea?
Right, so I mean, it's really hard to give you like a gauge invariant definition. I mean, people will point out, when a common horizon forms, right, that is, so I'm caution about the gauge aspect of that, but something like that is a point in time when the space-time changes qualitatively in it. Instead of being two distinct objects that have a whole lot more degrees of freedom, it's now it's highly perturbed, but it's a single black hole. And even though it's highly perturbed, it doesn't matter. You immediately lose a lot of degrees of freedom, and you can only then ring in this certain set of modes. Now, I'm saying that. There isn't any first principles theory that tells us that, but that seems to be what's going on.
Fair enough.
Okay, it is on. Just because you're talking about trying to get some physical insight into what you're doing, not just kind of perturb, and fit, have you been talking to Emory people about their end of things and trying to lock onto their physical intuition? And I know you're pushing toward Emory, but if you want to kind of really shoot for the stars.
Yeah, so something that we're talking a lot about within our group, and also with folks who do self-force in particular, I think there is a lever there that is not being fully leveraged in terms of telling us what's going on, in particular with the amplitude at late times as it comes into the merger, right? Where all the language of, Bob, we're going to map this to a perturber or a test mass coming in on an effective background space-time, right? It's a problem that self-force in principle can do pretty well. So that's one area where, yes, we're talking with those folks. I think I don't know, for other reasons, I'm not sure we would get to the Emery limit with this tool. That's why I'm sort of, let's start within reason, then maybe, yeah, absolutely, we can sort of try to push it and see how far we get.
Okay, great, thanks. Let's thanks Sean again. That puts us at the halfway point, so maybe stand up, stretch your legs while we switch to our next talk. Where are you? Alrighty, let's go ahead and get started again. So next we have Som talking about radiation boundary conditions and near to far field teleportation for the Teukolsky equation.
Before that, am I audible at the back without the mic?
Not online.
Okay. Okay, no worries. So, hello everyone. I'm Som. I'm a graduate student at UMass Dartmouth, working with my advisors Scott Field and Gaurav Khanna. And today I'll be talking about radiation outer boundary conditions. But not only that, I'll describe progress on a next generation time domain Teukolsky solver. And let's get started.
It's working now.
Okay, so to motivate the need for why we need to solve the Teukolsky equation in the first place, what we know is that LISA might detect signals from extreme mass in spirals, where we have like objects that are of stellar mass, which are inspiraling around a much larger black hole, like a supermassive black hole, at the center of a galaxy, like the system shown here. And we would need to test GR in the strong field regime because these systems would have a lot of orbits in the strong field. I'm packaging a lot into test of GR. What I really mean is, let's say, black hole spectroscopy, both like linear and nonlinear. You can try to do ring down modeling, QNMs, but I'm like packaging all of that in TGR here. And to achieve this, we would need very long and highly accurate GW templates. And we basically try to make these templates in the framework of black hole perturbation theory. And that is how we create these waveforms. Okay, so the Teukolsky equation is a central equation in black hole perturbation theory, and it describes perturbation. So for example, here you see the Teukolsky equation in its full glory, and the quantity psi here is called the Newman-Penrose scalar, which encodes the gravitational waves that we get. So we can calculate the gravitational strain from these quantity psi. There are a few quantities that I want to show here. That is the parameter A here, which is the mass of the central black hole. That is the curved black hole here. And for the present talk, I'm using A equals to 0. And then the Teukolsky equation becomes the Bardeen-Press equation. We are using spin weight -2, which basically means gravitational degrees of freedom. And T, the source term here, actually kind of models the particle that is inspiraling around this central curved black hole, or in this case, Schwarzschild black hole. Now, we are solving this using DG methods. I will talk more about DG methods in a few slides, why we are using that, what are its advantages, and so on. Okay, what is traditionally done, let's say, in a numerical solver for the Teukolsky equation? So the easier approach is to just place the boundaries very far away, in a way causally disconnect the boundaries. If we do that, what happens is your waves would not hit the boundary in the first place. The other way would be to, if we keep the boundaries nearby, then the waves would hit the solution and it would like pollute the physical solution. Now, at a given finite value of R, we do not know what the correct boundary conditions is for the Teukolsky equation. And it is specifically for the Teukolsky equation that if you evolve the simulation for long times, you see a kind of spurious growth at around times 1,000. So this is a typical S equals to -2 simulation. This is the final time of the simulation. You can see the ring down part, like a period of exponentially decaying solution, then the tail part, but then at late times you see this. This is not present in the Legge-Wheeler equation, only in the Teukolsky equation. So I'll tell more about this. So the reason behind that is called the long-range potential, and I can talk a lot about it. People are welcome to ask questions, but I would skip it in favor of more interesting results later. But this was studied in great detail by Oliver Long and Lior Barak in their paper. And again, they also see the same thing where you have time on the x-axis, and on the y-axis you have the solution, and at late times you see a t power 4 growth. So they are again like solving the 2-0 mode with s equals to -2. So this problem has persisted across previous investigations. So what are we trying to do here? We are trying to place boundary conditions at some finite value of r for the Teukolsky equation, and the quantities that help us do that are called these boundary kernels. So let me just explain the schematic of how we do that. So like I showed, we have a second order PDE in time and space, and then we Laplace transform it to get a second order ODE in space in the frequency domain. Here we use the outgoing solutions of this ODE to construct these quantities called boundary kernels, and then we inverse Laplace transform to get boundary conditions for the PDE. So this is our goal. Now I can talk a bit about how this boundary kernel looks in the frequency domain, but these are like technical details which I would skip, but people are again welcome to ask it. What I wanted to show though is how do we implement it in practice while constructing our Teukolsky equation solver. Okay, so we start by just separating the angular part. Because we have spherical symmetry, we can just separate out the theta phi using harmonics, and then we just have this function. And then we introduce auxiliary variables like w plus and w minus here, and write a system in 1 plus 1, or there is one dimension in space and time, and they are color-coded like this. So what we need is essentially boundary conditions for the left moving characteristic. So the right boundary is, let's say, some r equals to 100 or 500. We want the characteristic or the solution, or the characteristic that is moving inside the domain there. So whatever lives outside can be left untouched, essentially. So we discretize the system in tortoise coordinates, that is r star here, using our DG method. Okay, so how do we calculate this characteristic at the right boundary? So the characteristic that is coming inside is w minus, as I was showing here, and the quantity. This is actually the boundary kernel that we are actually convolving with the solution at the right boundary. So this can be any point actually that is RB here, but essentially we are doing a convolution here to calculate this characteristic which we supply. And our simulations use these kind of initial conditions here. This is like just a Gaussian pulse or a bump here with these like variance and the mean. And these are our parameters for the simulation. Our right boundary is at 120 m. Here. So just to show what happens when we put the boundary condition, so this is the simulation before putting the boundary condition. So one thing to note is I've put the right boundary very far away in tortoise coordinates, that is 1400 here. You can see in the right simulation the right boundary XR is very near. This is just 128, and final time is like even more than 2000 here. But the point is that you get a very clean power law decay, which we expect from Price's law, and we see a blow up in this case. People might think that, but this kind of just affects the tail regime here, as you can see. But notice that I'm only showing L equals to 2. What I mean is if you do higher L modes, for example, L equals to 4 or 5, the ring down regime here would persist much lower in solution value and in time. So basically, the ring down would also continue in this region. But the point is that if we do not get a correct long time evolution, higher L modes might be compromised because they would persist at lower solution values and longer times. Okay, so once we have that, how do we validate this? So what I'm trying to show here is, I mean, kind of as GW modelers, we want the solution at null infinity, not only at some finite value of R. And to do that, we create another type of kernel called the teleportation kernel. And what it is essentially doing here is, if you have the solution at some value of R, which is RB here, you can teleport the solution to null infinity. Okay? So this quantity phi is actually the teleportation kernel. You're again convolving it with the solution, and you get the solution at null infinity. Okay? How do we check that this entire procedure is correct? I'm showing the solution plotted as time in this figure. This is the solution at null infinity, the teleported signal in blue, and orange is the signal at finite R. And what we know from like analytical results by this result by Richard Price is that the solutions fall off as a power law. So this falling off as a power law in a log-log plot essentially means you approach a straight line. Okay, so what I'm showing is this, this orange plot should approach -7 here. That is like, it falls off as t power -7, so LPI is -7, but the solution at null infinity decays 1 power slower, which is -6, and hence the solution approaches -6 at large times. This is a kind of a validation for the method. But again, so we want to get gravitational waves. So all this is good, but we want to model in spirals. So coming to that, I will tell how are we basically getting energy fluxes and waveforms. The idea is to not overwhelm with equations, so there are only a few things again here. So essentially these quantities are, so we get these from the energy momentum tensor, and this is where the information about the inspiraling particle comes into the system. Essentially this quantity appears on the right-hand side of the PD that I showed. The upshot is this entire mess of a thing can be expressed as this kind of a, in this way where these are like constants and we are modeling circular equatorial orbits, so we have pi/2 and r0 here. Once we have this, I want to talk about how essentially we are implementing a particle in the DG method. And I want to emphasize it using a simple advection equation example. So here, if you have an advection equation of this form, where on the right-hand side you have some time into delta derivative, you can change the dependent variable and get an equation which does not have delta derivatives. For example, this was first power of delta, you have no delta here. Once you get an equation of this form, you can modify numerical flux. So maybe I can explain this a bit. So in DG method, you divide the entire computation domain into small chunks, okay? And you communicate information in between these chunks using the numerical flux. So what we do is to model a particle, we place the particle between two subdomain interfaces, and then we change the numerical flux in this interface. And this, in a way, resolves the problem because in typical time domain solvers, you model the particle by a very narrow Gaussian. So that essentially alleviates that problem. So the idea here again is to show the entire pipeline in one slide. The upshot is that we solve a matrix of equations of this form where you have delta functions on the right-hand side. Then once you have the solution at a finite value of r, you can teleport it using the teleportation kernels. Once you have the waveform at null infinity, you can calculate the energy flux using this method. Now, the final result of that is when you try to do circular equatorial orbits, we compare our value with the frequency domain result, and we get 10 digits of accuracy compared to the frequency domain results. So we get this E dot frequency from the black hole perturbation toolkit, and this is like the particle is at 10 m, and we are just looking at the 2-2 mode here. So to conclude, the paper for the homogeneous case is on the archive, you can see here, and to take this further and to introduce more physics into it, we would like to do this for the Kerr spacetime because that is more astrophysical, and then we would want to do this for eccentric and even more physical orbits, like for example, plunge and zoom wall orbits as well. That would conclude my talk. Thank you.
Thank you, Som, for that excellent talk. Any questions? Come to the center, please. Anything online yet? Okay, great. Well, then I'll start with mine. So the radiation boundary did seem very effective at removing the extra kind of noise at the end. So it's kind of null question because it already is being fixed, so it doesn't super matter. But I do just wonder how significant that extra noise is. You mentioned it could potentially affect higher modes and stuff, but it's at such a quiet amplitude. Is there any chance of that actually being observable or mattering in data analysis?
Yes. I think the tail part, like for example, like realistically speaking, the tail part might be very difficult to detect because it's a very long time effect. Like you would have ring down and then the signal would decay further and like you'd observe the tail much later.
What's the time, when you say much later, how
much later is, I don't know, like in powers of m, I have 100, 500 after merger kind of a situation. So yeah, so I think it's a very long time effect for the homogeneous part where you have the ring down. But the same problem can come in the inspiral part when you are solving the inhomogeneous Teukolsky equation. Okay, so for example, if the problem appears there, then you would not get like very large number of orbits in the inspiral because your time domain solver is not working correctly for large number of orbits. Yeah, so it depends on like if you're talking about the homogeneous Teukolsky equation or the inhomogeneous Teukolsky equation as well. Yeah.
Okay, thank you. Any questions? We have just a minute. All right, then let's thank Som again. Okay, next we have Jann giving us a talk on towards claiming a detection of gravitational memory with Lisa. Go ahead and take it away.
Yeah, thank you very much. Is this working or?
I think so.
Now it should work. Okay, perfect. All right. Yeah. So actually, I want to start this talk with maybe a bit of a provocative question, just to spark up the minds a bit in this afternoon session after lunch. So the question is, where do you think that we should look for new physics in general? And so I guess from an effective field theory perspective, it is very clear that the unknown should lie in the small scales, the high energies, the UE physics. But it appears that many of the biggest open puzzles in physics actually reside in the opposite limit, it seems. So on large scales, so for instance, on cosmological scales where central observables seem to be in tension with our theoretical understanding, the cosmological constant problem, or maybe even the information loss in the behavior of large-scale black hole spacetimes. And in this EFT paradigm, one often assumes a fixed background, but actually in the last couple of decades, we have more and more understood that the IR of field theory is actually governed by a very non-trivial, universal and also dynamical structure. So I will not go into details here, but perhaps you have already heard of the infrared triangle. And I guess the exciting thing is that Lisa might be able to actually probe this low energy sector of field theory through what is called gravitational memory that we already heard about in the first talk of this session. So in this talk, I want to give a very brief overview of this story of the connection between these two triangles, sort of. So yeah, and to start, I want to remind you or tell you what gravitational memory is. So we already heard a bit of it, but I want to go a bit into more details so that we are all on the same page. So for this, let's consider a localized source that emits gravitational radiation, like depicted in this Penrose diagram. And for concreteness, let's talk about the binary black hole for this Lisa talk. And so as you all know, as the binary is spiraling, this periodical motion emits radiation in the form of gravitational waves, as depicted here in terms of this H+ polarization. But GR actually tells us that on a very fundamental level, this is not the full picture. And this is because these waves themselves carry energy momentum, and there's a back reaction effect of an emission of this energy momentum that causes here this radiation here in this polarization to have a non-zero offset here. And this is what a gravitational memory is. So radiation actually always comes in two components in this very simplified language. There's a wave component and a memory component. And what does that mean physically? So if we have a waveform that now actually accounts for the memory offset, if we send this into a ring of test particles, which is like a prototype of a detector, what happens is that we have the usual oscillations of these freely falling test masses, but the fact that there is a non-zero memory means that this ring of test masses will never go back to its original shape. So in this sense, space-time is permanently deformed, and so memory could be described as the scars in the fabric of space-time that remember the passage of gravitational radiation. So yeah, so this is actually a prediction of GR that hasn't been measured yet. And I guess the reason why I'm talking to you here in this LISA symposium is that LISA might actually provide the first single source detection of gravitational memory. And I think, so at least from my point of view, this would really be one major achievement that the LISA mission could bring us. And this is also why there's a whole group of people in the fundamental physics working group that are working towards this goal. Now I will not have the time to describe all of the results that we already have, also in recent publications, but I will give you two of the most important ones. And so one is, that was already mentioned, the necessity to have a good memory model in order to actually be able to claim a detection of memory. And the other will be just an assessment of first detectability prospects using a Bayesian factor analysis. All right. So with this, let's try to understand how LISA can actually measure memory. So here you have a basic waveform of a binary black hole merger, a super massive one. And so, yes, just by looking at this waveform, it might actually, there might be, you could think these are really good news because memory, as you see, is in terms of amplitude quite a large effect. So you really see it by eye. The scale of the amplitude is almost as big as in spiral. So yeah, it's in amplitude, it's a very large effect. And so with our hearts full of hope, sort of, we plug this waveform into the LISA response. But then we see that, oh no, in the LISA TDI response, the memory is actually completely gone. And this is not a specific fluke of LISA. It's just the fact that any gravitational wave detector that is limited in its frequency band will never actually measure the permanent memory offset. However, not all hope is lost because what we can still measure is the transition. So the transition between one state to the other could leave an imprint in our gravitational wave detector. But the question is then, how can we actually model this waveform, or what part of the waveform can we uniquely associate to this memory offset? And just to give a feeling of the problem that we have, we can go through a few examples of what we could try. So the first thing that could come in mind is just a step function at the merger. But of course, it's a very crude model, and it's even UV divergent. So when you resolve these timescales, it's not a good model. Then you could come up with some smoothing out of this step function. But of course, there it's really not clear, okay, where do you place this step? And how smooth should it be? And maybe there's someone else that takes the connection between the infrared triangle and LISA too literally and could come up with something more creative. Who knows? But of course, the point here is really that if we don't have any additional input, physical input, it's really not clear how we should model this. And so our proposal, it was already mentioned, is actually quite intuitive. I think if we look at this example that we had in the beginning of just the in spiral, because we have really these two components, the gravitational waveforms whose dominant frequency is really tied to the orbital motion of the binary. And so this red curve, how can we get this? It's really if we do an averaging, so if we know the frequency and we do a space-time averaging, or here time averaging, over these frequency scales, we would get this sort of background change that we can associate to the memory. And so there's actually a whole formalism that was developed actually before the description of memory. The Isaacson approach that gives you the tools to do this. And in the real life scenario of a binary black hole merger, we can be a bit more sophisticated and actually solve the low frequency equations to get this formula. And so for the experts here, this formula is really equivalent to the null part of the BMS balance law, so you have the same memory memory offset, but the difference is here that you plug in this so-called Isaacson energy momentum, which is a coarse-grained version of the energy momentum tensor, which takes into account that it only makes sense to define energy up to certain amount of wavelength. And with this, you actually mitigate any kind of residual oscillations that might still be there that are not really associated to the final memory offset. So here we have the memory model that we wanted, this red line here, and so we can go back and plug it into the LISA response. And so we already see here that there will only be any non-trivial frequency effect in the response around merger, and this is exactly what we see here in the LISA TDI response. So memory is really just a burst around merger, and we can actually understand this shape here by just knowing that the TDI actually acts at low frequencies as a third derivative, and this is just what we see. This is just the third derivative of this signal here, and so because it's a derivative of a low frequency signal, of course, the big amplitude that we had in the beginning is now very small. This is the reason why it's really hard to detect memory with our detectors. But yes, for LISA, the supermassive binary black hole, mergers are so loud that we even get significant amount of SNR for memory. And so, yes, I will not go into detail here, but the study that we did over many parameters, parameter space is that in this setup, we really, by computing the actual base factor, so comparing a hypothesis of having memory and not memory, we can claim a memory detection if the SNR is above 5. So in this case, we would have, can be sure that the base factor will be, the log of the base factor will be above 2. So it's like 100 times more likely to have memory in the data. And you see that in this, for this specific set of parameters, which is actually an average inclination angle, we can already measure memory up to redshift of 4, which is quite a long range. And so this is really, I think, the main message here is that even if we also look at the actual population models for these massive black hole binaries, is that many models, especially the heavy seed ones, we get a high probability of having an iteration where we would detect memory with actually quite high SNR. So we're not just scratching the boundary of detecting memory, such that there is room for a realistic prospect of detection, even in the full scenario of a LISA global fit. So yes, with that, I want to conclude. And so we are, yes, we really think that it is a real possibility that LISA might be able to claim a first detection of a single source memory event. And yes, this is also why we are, will work hard on this task also in the future. And yeah, so with that, thank you very much, and I'm happy to answer any questions.
Great, thank you. Any questions? Please come to the center. Thanks.
Hello. Yeah, taking advantage of being close to the mic. Hi, I'm absolutely not an expert, so this is probably a very naive question. I'm very fascinated by memory, so could you explain to me why LISA can't see this offset in the amplitude? What does it have to do with the frequencies? What's the explanation for that?
So the basic reason is quite simple. It's just that having this permanent offset in terms of frequencies is really so. It's really the time scale of your signal is really the frequency of your signal, and because it's a permanent offset, so if you take the actual limit, it's a zero frequency limit, and so the problem of LISA and actually any gravitational wave detector is that it's just that the sensitivity is just limited to a certain frequency band, and so you can imagine that right, memory you would observe in this idealized case in the ring of test particle by comparing how the ring would have been before and after the burst has passed. But the fact that we only control a certain frequency range means that we actually don't control the test mass so well on such a time scale. So it's just on this time scale, we are just swamped by noise, and so you will not be able to compare the beginning and the end. And this is the basic reason, which is a bit annoying, but yeah.
Thanks for the very nice presentation. I would like to ask if you know how this forecast for LISA translate into ground-based detector forecast for
well, it will not translate one-to-one, but the ground-based, at least the next generation ground-based detectors are also are in some sense even better for detecting memory due to various technical reasons. But I guess ultimately it really depends on the SNR that you have for the whole signal, the full signal, and if this SNR is loud enough, you will also be able to detect memory. So memory will also be a deal for next generation ground-based detectors.
But loud enough compared to what? Because there will be also subdominant effects from other physical effects that will be in your waveform. So what does it mean, loud enough?
I think we're going to have to call it there and discuss that during coffee break, because we're over time and that's a heavy question. So let's thank Jann again. Okay, all right, thank you everybody. We have I turned it off. Okay, we have our last talk today by Varenya talking about error quantification for numerical relativity surrogate models. Thanks.
Hello, my name is Varenya Upadhyaya, and I'm a grad student at the University of Massachusetts Dartmouth, where I work with my advisors Vijay Verma and Scott Field. When we have gravitational data come in, we usually have some time series data which can be thought of as a summation of some physical signal and then some noise. What we then do is we take please ignore the formatting, the Google Slides to PPT did not work. But then we take some waveforms inspired by general relativity, and the hope is that those edges are very similar, very close to the physical signal that we're seeing. And these are typically functions of a 15 or more or less dimensional parameter vector, lambda. At the end of a PE run, typically what we have is a probability distribution of these parameters given the data in our model. And these are given very nicely the pointer isn't working.
Should be on the bottom.
Oh, it's the wrong button. Okay. By the Bayes theorem, where you have the likelihood, the priors, and the evidence. This is good because now we can get an understanding of what our system looks like, and we have uncertainty estimates as well. But more importantly, with these, we get to make the biggest corner plots in all of astronomy. Okay, now with next-gen detectors coming up, we're going to need much higher, much more accurate models because we're going to be seeing signals with much higher SNRs. And the reason we need higher accuracy is mainly twofold. The first one is because as you increase SNRs, your posteriors become sharper, and posteriors that initially would have contained the true value of parameters because of uncertainties might completely miss them as your SNR increases. And you can thank Deborah for this animation. The second one has to do with this plot from Purer and Haster that makes a lot of NR people very nervous because it essentially says that for these models to be usable, we're going to need 6 to 7 digits of accuracy. And now 6 to 7 might sound a little excessive from a data analysis point of view, but the idea is that when we do tests of GR, we want to be very sure that any deviations we see are physical and not just because our waveform models aren't accurate enough. With that as the motivation, here's what we did. We took NR waveforms generated using the spectral Einstein code. And these are great because they're very accurate, but the issue with them is that they're very, very, very expensive to generate. One simulation can take months to get, and doing data analysis with that would be horrible. These also come in different resolutions that are referred to as LEVs. So a LEV 3 NR simulation would be a higher resolution than a LEV 2 NR simulation. Then we use surrogate models, which effectively interpolate this waveform on the parameter space grid. So if you have a few parameter space points for which you have the NR simulations, you can use the surrogate model to get a waveform anywhere within that grid. The model we used is called NR-Sur 3D-Q8, which is an aligned spin model which has 3 dimensions, so 3D, and it goes up to a mass ratio of 8. And these are typically trained on the highest resolution data, which in our case happen to be the LEV 3 data. Now, we essentially started with like a thought experiment. Imagine that you live in a world where there's no LEV 3 NR simulations, and you only have access to the LEV 2, which is the second best NR simulations in our case. What would happen if you then trained a surrogate model with that, did some PE or data analysis, injecting a LEV 3 or a real ground truth NR signal? The idea is that if we can try to understand what kind of biases happen as you go down one LEV, we can try to figure out what kind of biases we're missing out, we're having already by not having a LEV above where we are. And so with that, we made 2 models, a LEV 3 and a LEV 2 NR-Sur 3D-Q8. We use aligned spin priors, then we did some PE runs using Dynasty, which was then called through the Bilby interface. So this is one of the main plots from these PE runs. And here you can see chi-effective and mass ratio plot on the Y and X axes. And in black, we have the high resolution or the LEV 3 model, and in red are the LEV 2 posterior results. The yellow is the injection, which is essentially the true parameters that we injected. And you can see that the lower resolution one biases towards mass ratios of 1, whereas the LEV 3 model essentially picks up on the true parameters. Now, one guess that we have about why this is happening is because as you reduce NR simulations, your orbits shrink because you have to account for more energy being lost in lieu of some numerical errors. When you have more energy being radiated as you have lower resolution simulations, you end up with shorter orbits. From the data analysis point of view, though, shorter orbits are also achieved when you have systems with mass ratios of near 1. So everyone knows that MREs have multiple cycles and they have much longer orbits. But as you have mass ratios going closer to 1, those orbits will also be smaller. So it's sort of like these two effects are canceling each other out, and they give us completely biased results. And that would be horrible if this happened with real science. So we're not also the first people to look into folding errors into PE. The EOB and Phenom models usually have some calibration parameters that are used to improve accuracy by taking NR as references. And so instead of having those as fixed parameters, you could use them as free parameters and then marginalize over them during your PE. Another way to do this is just to have a model agnostic error system setup where you essentially sample from a normal distribution for your phase and amplitude errors. And then with the sampling, sampled values, you just put that into your waveform model and then you do your data analysis. The one that was most applicable for our case is to come up with some estimates of what the model errors might actually be like, and then to use that to sort of inform how much statistical bias we're essentially missing out on by not including these errors while we're doing data analysis. So with that being, this also didn't format properly. So for the model that we had, the 2-2 mode can be decomposed into the amplitude and the phase, like so. And the phase errors are typically 2 orders higher than the amplitude errors. So we define the phase errors as the difference, so it would be a time series, which would be the difference between the LEV 3 NR simulation, which we can think of as sort of a ground truth phase, and the phase of the surrogate, which is the best model we have. The idea then is to build a another surrogate model to essentially predict this time series at any new parameter space point. And so what this looks like is this, and this might look very concerning to people who do waveform modeling because the reds don't track the blacks. But it's important that they don't, because if we have a perfect error model, then that means that our waveform model to begin with had some artifacts that it didn't take full advantage of, and these could potentially be used to make that model better. But the idea here is that we want our error model to sort of track and learn the general trends in what the model errors of the waveform model actually look like. Now, since since the red line, which is the predicted error, won't always be the actual error, what we can then do is we can make a probabilistic version of this, and then try to sample over that while we're doing PE. So instead of just having one thing, the idea is that any one of those red lines could be a potential realization of what the actual error is. And now that we have a free variable error model, we can then use that to fold it into PE by marginalizing over those errors. Finally, I have some plots of what the error model actually does. This is a plot of the error versus the two spins of the black holes. And as you can see, there is not much structure to either of the errors, but the important part is that the reds track the blacks roughly. And so where the blacks go down, the reds also go down, and then that trend is seen roughly across the spins. The more interesting one would be this histogram, which essentially has the L2 norms of the true errors and what the model actually predicts. And then on the right, we have the errors versus mass ratio. And it's also a known fact that as you increase mass ratios, your phase errors would go higher. And that's also sort of what we're seeing here with the error model. It's not as noisy as the true errors, but the fact that it's picking up on the idea that increasing mass ratios increase errors gives some confidence that you can potentially use this in your data analysis for. And that brings me to the end of my talk. The summary is up there, and for the future work, the idea is to then now actually do PE with this error model, and then to also extend this to model the amplitudes and also higher order modes, because things get more and more complicated as we go higher. Then frequency domain error analysis is also something on the horizon, and then the end product of this entire project would be amazing if you could actually come up with the error model for the actual surrogate models that we have for maximum science applicability. Thank you very much.
Okay, great. Any questions? Please come to the center. That's a movement. Grace.
Thanks for the nice talk. I was wondering if you've tried doing parameter estimation, marginalizing it. So whether you can comment on how much slower it is.
Sorry, marginalizing over?
So you've built this error model for the surrogate model, and obviously what we want to do then is to marginalize over that error model when we're doing parameter estimation. Yep. Have you tried that yet? And if so,
yeah, so we have some runs. They're not final enough to show in presentations. It didn't cause too much of a slowdown. Maybe a factor of 2 is what the overall time was increased by, but it wasn't
just doing, so each waveform evaluation you do one random draw from your error model, or you do so?
Yeah, so there's two ways to do this. So a lot of LIGO data analysis also has these calibration parameters for detectors, and those can go up 20 or 30. But if they have good structure, then you can marginalize over them very quickly because you land on what the actual the most ideal parameter value would be very quickly.
All right. Yeah, go ahead.
Thank you for the very nice presentation. I would like to ask you have you checked if this model captures systematic mismodeling of the surrogate, for instance the use of the SEBOB before HM for the hybridization instead of SEBOB B5HM, if you have checked this for low total masses or not?
So are you asking if we've checked if this general methodology works for SUB and RB5 PHM? Or?
I am asking if you have maybe checked, because this is a hybrid surrogate model, no? Calibrated to a certain part, hybridized with hybridization procedure that may introduce some systematics. I'm wondering if your error model captures this kind of systematics.
Yes, so these error models are just for NR-SUR 3DQ8. We haven't gotten to the hybridized model yet. So all these error models are essentially just as long as the NR simulations. So no hybridization yet.
All right, great. Let's thank Varenya again. And then now I think we have our our break. I think the next parallel session starts at 4. Correct me if I'm wrong. Okay, great. So we've got 22-minute break.